In this lesson, we will answer one precise question. If the x partial derivative of the two-variable function exists at a point, what kind of continuity follows? The answer is useful, but limited. Continuity along one horizontal cross-section at that point. Let z equal f of x comma y, and focus on the point P0, with coordinates x0, y0. The value f of x0, y0 is the height of the surface above that point. We want to understand exactly what the x partial derivative controls. Does it control the whole surface near P0, or only a particular way of moving through that point? The definition itself will tell us. To take the x partial derivative, first freeze y at y0. Imagine placing a vertical sheet through the surface along the line y equals y0. That sheet cuts out a one-variable curve. A nearby point used by the x partial derivative is x0 plus h, y0. Only x changes. The second coordinate remains y0, no matter whether h is positive or negative. Here is the controlled cross-section. The blue horizontal line represents y fixed at y0, the center is P0, and the nearby blue point is reached by changing x by h. Every difference quotient stays on this one line. Give this cross-section its own name. Define g of x to be f of x, y0. Once y0 is fixed, g is an ordinary one-variable function. This simple renaming exposes the entire argument. Now write the limit definition. The x partial derivative at P0 is the limit, as h tends to 0, of the change in f along the fixed y line, divided by the change h in x. Because g of x is defined by freezing y, g of x0 plus h is exactly f of x0 plus h, y0. Likewise, g of x0 equals f of x0, y0. Substitute those two expressions into the partial derivative. The formula becomes the familiar one-variable difference quotient for g at x0. Nothing two-dimensional remains inside this limit. So the x partial derivative of f at P0 is exactly the ordinary derivative of the slice g at x0. Existence of the partial derivative means that g' of x0 exists as a finite number. We have reduced the problem to one variable. The cross-section g is differentiable at x0. A basic one-variable theorem now says that differentiability at a point forces continuity at that point. Let us see why. To prove continuity of the slice at x0, our goal is that g of x0 plus h approaches g of x0 as h approaches 0. Equivalently, the change in g must approach 0. Call the difference quotient q of h. Since the derivative exists, q of h approaches the finite number g' of x0 as h approaches 0 through non-zero values. Multiply the quotient back by h. This gives an exact identity. The change in g equals h times q of h. The formula separates a very small horizontal step from a quotient that settles near a finite number. The first factor is h itself, so it approaches 0. This is the shrinking distance between x0 plus h and x0. The second factor approaches g' of x0, which is finite. It does not blow up. Intuitively, the local rate of change settles down while the step size shrinks to 0. A quantity approaching 0 times a quantity approaching a finite number approaches 0. Therefore, h times q of h approaches 0. This is the precise reason the change in the slice must vanish. Using the identity, we conclude that g of x0 plus h minus g of x0 approaches 0. Nearby values on the slice must become arbitrarily close to the central value. Add g of x0 back, we obtain g of x0 plus h approaching g of x0. That is exactly continuity of the one variable slice g at x0. If you want a size-based proof, a function that approaches a finite limit is bounded nearby. So for sufficiently small non-zero h, the absolute value of q of h is at most some fixed number m. Taking absolute values in the identity gives the change in g at most m times the absolute value of h. Since m is fixed and h shrinks to 0, the squeeze theorem forces the change in g to 0. Now translate the result back to f. As h approaches 0 while y remains exactly y0, f of x0 plus h, y0 approaches f of x0, y0. This is continuity at p0 along the horizontal line y equals y0. It is a genuine continuity statement, but its domain is the one-dimensional cross-section selected by the partial derivative. One precision matters. Existence of the partial derivative at p0 proves slice continuity at x0. It does not automatically prove continuity at every other point of the line. For that, we would need the corresponding derivative information at those points. Full two-variable continuity asks for something stronger. The value f of x, y must approach f at p0 whenever the point x, y approaches p0, with no restriction on how it approaches. In the full limit, x may change, y may change, or both may change together. We can approach horizontally, vertically, diagonally, or along a curved path. Every sufficiently near point must cooperate. The arrows show several ways of approaching p0. Full continuity requires the same limiting value along all of them. The x partial derivative tests only the blue horizontal approach, where y remains y0. So one x partial derivative gives information about one selected slice. It provides no control over paths on which y changes. A bad diagonal or curved path can destroy full continuity without disturbing the horizontal slice. Here is a decisive example. Define f at the origin to be 0. Away from the origin, define f of x, y to be xy divided by x squared plus y squared. First inspect the horizontal cross-section y equals 0. Substituting y equal to 0 makes the numerator 0, so f of x, 0 equals 0 for every x. This entire slice is the constant 0 function. The x partial derivative at the origin therefore exists. Its difference quotient is 0 divided by h, which is 0 for every non-zero h. The limit is 0, and the horizontal slice is continuous at the origin. But now approach the origin along the diagonal y equals x. For non-zero x, the function becomes x squared divided by 2x squared, which is 1/2. Along this path the values stay at 1/2. The horizontal path gives limiting value 0, while the diagonal path gives limiting value 1/2. Because two approaches disagree, the full two-variable limit at the origin does not exist. This example proves the distinction. The x partial derivative exists, and its chosen cross-section is continuous at the origin. Nevertheless, the full function is not continuous there because another direction behaves differently. Here is the correct implication. If f sub x exists at x0, y0, then the one-variable slice g of x equal to f of x, y0 is continuous at x0. Here is the incorrect implication. To avoid existence of that one partial derivative does not imply that f is continuous as a two-variable function at p0. One controlled slice cannot certify every possible approach. The key way is simple. Existence of the x partial derivative guarantees continuity only on the x direction cross-section. At the point where the derivative exists, it does not guarantee continuity of the full two-variable function. Always ask which variables were allowed to move.